Everybody, good evening. So Camilo and I work together for the same company. It's a small technology company called Oledcomm. And now I moved to the Laboratoire National de Métrologie. So we were interested on designing optics, and in this case it were optics, very, very complicated optics, because we should capture a lot of light into a small photodiode, in an avalanche photodiode, in fact. And these lenses are called parabolic compound concentrators, yes. So it was our motivation. Then we saw that things didn't work as we expected. So normally we have in optical design that lenses for optical designing we have some variables very useful. For example, the focal length, the distance from the lens to the object, to the image, some planes that are called principal planes, and the height of the image of the object, and also the thickness. And in addition to that, there is the thickness of the lens, and in addition to that, there is also the index of diffraction. Now we have working on that, as we have not the expensive, very, very expensive software used for designing, as is Code 5, 12,500 euros for one license for one computer for a year. Nor CMAX, same quantity, but for forever. So we decided to start with our own method to calculate the surfaces. And I'm going to talk about the state of the art. There is a French scientist that works in optical design. In fact, there are two designers, very, very well known all around the world. One of them is a former suboptic. It's Jean-Luc Roland. And he's the chief of a group in a laboratory in the United States, in Rochester University. Their approach to design freeform lenses is this one. We get a surface, base surface that contains becoming constant, and she adds, well, the community adds a polynomial to include deformations to the lenses. With these deformations, we come to compensate the aberrations of a lens. This is an example of a design that was published in Nature Communications last year. And they obtain, here for example, with 3 mirror, they obtain this map that encodes the aberrations point by point in a field of view of 2 degrees, plus minus 2 degrees. That means that all is diffraction limited because this is the scale. That means that all the light coming from an object is imaged here with very, very good specifications, limited by diffraction, at this small angle. It was a problem not at all as we have, because we needed 20 degrees, 35 degrees for acceptance angle for our project. So, and we should put all the light into an optical fiber. So it was a problem almost impossible. So I'm going to talk first of all about how it was conceived, the design before. For some 400 years, the optical designers follow these two models. This is a first approximation that takes into account rays that have a very, very small angle. So the sinus of the angle is substituted by the angle. And this is paraxial optics. The other one takes into consideration the theory of aberrations. And, well, this is the construction. The stop pupil could be everywhere. And there are two rays, very important. The first one is the shift ray that crosses the optical axis here in the intersection with the copy. And the second one goes through the margin of the pupil. But how about removing the optical axis? Well, in fact, we were desperate. So we were doing a lot of ideas, etc. And we decided to remove the optical axis because it was very stringent. And normally we have in the optical axis the reference point. Now the reference point is aside. And if we get some vectors, for example, P0, O1, P2, P3, we can take our reference with respect to these vectors, not to the optical axis, or to the focal length, or so on, so on. And in addition to that, we said, well, we need a perfect image here, because aberrations, every system has a lot of aberrations. What's the condition for having here an image with no aberrations? That's the point of freeform optics. So we have here some differences between position vectors, the vectors P, O, P, P, etc. And this is going to give us our arbitrary vector. And we have here three arbitrary vectors. This one in the middle of the lens, and this one. And with that, we have three reference position vectors, and the respective, three position vectors, and the respective three reference vectors that will give us information about these segments. So we call that an optical path. Our proposal was accepted for publication in Applied Optics and is coming very soon. But so we count now with only two main laws. Well, one of them is a principle, the principle of Fermat. The second one is the Snell-Descartes law. As for the first one, we should take care that the signs used in Fermat principle respect absolutely all the four cases possible in lenses. This is the real object and the combination of virtual and real images, and the virtual object and the respective combination of images. Now, we want to obtain a vector V1, a vector VO, and the normal, and the word normal is very important here because it will ensure us that no aberration exists. And we are going to relate these, they are related, in fact, with the position vectors, with the vectors, the arbitrary vectors, and what else? And with the, n that is there. Now, finally we have two results here. This is our good result. And from here we can get to this result. This is for refractive surfaces. This is for reflective surfaces. We have related our second position vector, the second surface, with the position vector of the first surface and with the arbitrary vector that is between the first and second surface. And we get this. We have here a very complex system, and the person who have worked with optics can know here, can see here that there is not an optical axis, that there are two surfaces that are not parallel between them. One is tilted with respect to the other, and in addition to that, we have here a tilt between this surface and this surface, sorry, not a tilt, a prism. So normally, an optical designer could say, well, you are going to have three aberrations. First of all, spherical. Second, comma, because it's an off-axis system. And third one, astigmatism, because these surfaces are not parallel. Not only tilted, but oriented in different, following different axes. But this is a real calculation. This is not merely made with a rule or something like that. This is calculation in Mathematica, sorry. And we have a perfect image. And when I said that we need to know the normals of the surfaces, it's because imagine this lens. Here I decided to include a second point because it's easy to have, well, relatively easy to have an image free of aberration, spherical aberration on axis. But in the image, in 2 points in the image, it's not so trivial. So to guarantee that, we first of all obtain the second surface, and then we include the second point, this point, and we are going to obtain a second surface that will intersect the first one in this point, in PO, in P2, if the normals of both surfaces are parallel. Then we are going to have a free aberration surface here, image here. I'm finished. This is another example. Here you can see that there are a lot of rays. This is a real calculation. And we compare the surface obtained here with a surface, cervical surface. So the error between both surfaces are very, very, very small. So we are in the Armstrong order, but this is scale millimeters, so it fits perfectly. Now, the last part of our research was how to pass to go to production of lenses, because this is the point. And well, we should our surface that is represented parametrically. We can convert that in expression, but it's an expression of how many pages? 60 pages. So to put that into the machine is messy. We should send the cloud of points to the machine, and to guarantee that the surface has a good quality, we can use a lot of points. In this case, there are 500 points. Here, 500 or 100 points. And look that the error is very small, 6 nanometers. And this is perfectly manufacturable. This is the object of another article that is approved, so it's going to be published in this month. And finally, this is the last slide. We have the cloud here of points. We should filter all the points, then create the surface, and to include this surface into the patch of the surface. And now Camilo is manufacturing a lot of lenses for products. And well, this is all. Thank you for your attention.